In this video, we are going to be learning about the formulas for the different types of energy. We're going to start with kinetic energy. The formula for kinetic energy is kinetic energy equals 1/2 mv squared, where the m stands for the mass of the object and the v stands for the velocity or speed of the object. Notice that it's the velocity squared, which means that the velocity will make much more of an impact than the mass does. Please copy down these examples in your notes. A 10-kilogram sled has a speed of 2.2 meters per second. What is the sled's kinetic energy? So this one's pretty easy. You just plug in 10 for the mass and 2.2 for the speed. So you end up doing 1/2 times 10 times 2.2 squared, and you get 24.2 joules. Notice that the units for energy are joules, same as they are for work. Second example, a 2-kilogram projectile has a speed of 30 meters per second. What is its kinetic energy? We're going to plug in 2 for the mass and 30 for v, the speed. So you end up doing 1/2 times 2 times 30 squared, and you get 900 joules. Notice real quick that even though this projectile has less mass than this sled, it has a lot more kinetic energy because its speed is more, and that speed is squared. Last kinetic energy example. A 70-kilogram stuntman jumps from a high bridge into a river. Just before he hits the water, his kinetic energy is 34,300 joules. What is his speed? In this problem, we are not looking for the kinetic energy. We are looking for the speed. So we're going to have to start at the very beginning here with the formula. Kinetic energy equals 1/2 mv squared. Now we're given the kinetic energy. It is 34,300 joules. So we want to plug in this number right here. And then we want to plug in the 70 kilograms here for the mass. And v is what we're looking for. We're looking for the speed or the velocity. So I plugged in my numbers. The next thing I'm going to do is I'm going to do the 1/2 times the 70. 1/2 times 70 is 35. So we end up with 34,300 equals 35v squared. The next thing we want to do is divide both sides by 35, so we can get that v squared by itself. And we end up with 980. The next thing we want to do is take the square root of both sides to get rid of that squared on the v. And you should end up with v equals 31.3 meters per second. Meters per second are the correct units for speed. Now, as you may recall, there are two types of potential energy, gravitational and elastic. So we have two different formulas. For gravitational potential energy, the formula is GPE equals mgh, where m is mass, g is acceleration due to gravity, and h is height. G will usually be the number 9.8. If you recall from the free fall lab we did, G equals 9.8 meters per second squared. Then we have elastic potential energy is 1/2 kx squared. K is the spring constant, and that measures the spring's resistance to being compressed or stretched. The units are newtons per meter. So basically, this spring constant tells you how difficult or easy it is to stretch or compress a spring or another elastic object. I'll probably be showing you some springs in class so you can see springs with different spring constants. And then X is the amount the spring or elastic body is stretched or compressed from equilibrium. So make sure you have all this information. All right, we're going to do 3 sample problems for gravitational and 3 sample problems for elastic. Here are the ones for gravitational. Sample problem 1. A stationary car with a mass of 1,500 kilograms sits at the top of a hill, the height of which is 15 meters. What is the gravitational potential energy? So, we just do GPE equals mgh. We want to plug in 1,500 for the mass. Remember, G will be 9.8 on the surface of the Earth. And in this case, the height will be 15. So we just do 1,500 times 9.8 times 15. And that ends up equaling this number, which is 220,500 joules. So that's a lot of energy. All right, sample problem number 2. A 90-kilogram stuntman stands on a 50-meter high bridge. What is his gravitational potential energy? So again, we just do mgh. M is 90, G is 9.8, and H is 50. And we end up with 44,100 joules. Notice that the car has a lot more potential energy because its mass is so much more. So even though the stuntman is at a higher height, the car has a lot more mass. Sample problem number 3. A 4.5 kilogram cat's potential energy on a wall is 445 joules. How high is the wall? In this problem, we are not asked to find the potential energy. We are asked to find the height. So let's start at the beginning with the formula. GPE equals mgh. We are given the potential energy. It's 445, so we want to plug that in right here. We are given the mass. It's 4.5, so we want to plug that in for m. G is always 9.8. So we have this. The next thing we want to do is do 4.5 times 9.8. And that becomes 445 equals 44.1 H. And then we can just divide both sides by 44.1. And we get H equals 10.09 meters. And the correct units there are meters because it is height. Let's do our elastic potential energy sample problems. A spring has a spring constant of K equals 30 newtons per meter. It is compressed 0.5 meters. What is its elastic potential energy? So elastic potential energy equals 1/2 kx squared. We want to plug in 30 for K, because that's the spring constant, and X is 0.5. So we just do 1/2 times 30 times 0.5 squared, and we end up with 3.75 joules. Notice that it doesn't matter what type of energy it is, the units will always be joules. A spring with a spring constant of 52 newtons per meter is stretched 1.1 meters. Calculate the elastic potential energy stored in the spring. So, we plug in 52 for K, which is the spring constant, and 1.1 for X, because that's the distance from being stretched or compressed. So 1/2 times 52 times 1.1 squared equals 31.64 joules. And notice that this one is quite a bit bigger, has a lot more energy than this one, because it's being stretched a whole lot more. Last problem. A spring has a spring constant of 515 newtons per meter and is stretched 0.02 meters. So that's 2 centimeters, guys. Calculate the elastic potential energy stored in the spring. So we plug in 515 for K and 0.02 for X. So we do 1/2 times 515 times 0.02 squared, and we get 0.103 joules. Why is this so low? Well, the answer is it's not stretched very much, and that's going to end up making a big difference in the lack of energy. Please make sure you have all the examples written down and that you do your summary for your Cornell notes.